Right, good afternoon, Year 12 physicists. Right, last time we spoke, we started looking at the solids under stress unit, and we discussed the three types of solids. Let me just shut the door, apologies. We discussed crystalline solids, amorphous solids, and polymeric solids. Right, so I hope you remember the definitions of all of those. We looked at Hooke's law and how the extension in a spring or wire is proportional to the force applied to it. Who's this? Harvey. Hi, Harvey. Can you hear me? Hello, hello. And we looked at the graph. Yeah, awesome. And we looked at the graph and how it's a straight line graph until we reach what's called the elastic limit. And when you reach the elastic limit, then the graph changes and we have what's called a deformation. I think someone else tried to log in then, but I can't see them now. Oh well, never mind. I'm sure we all get in touch. Right. So what we're going to do today is look at something called the Young modulus, right? And this elastic constant from Hooke's law is great, but imagine you have, a piece of rubber, right? If the dimensions of that rubber change, the amount it will extend will change. If it's thicker, it'll extend less. If it's longer, it would extend more. So what we need some way of getting like a spring constant for a certain type of material independent of its dimensions. And that thing is what's called the Young modulus, right? So I'll just read the sentence here. It would be far more convenient if we had a constant for a particular material which would enable us to find extensions knowing the constant and the dimensions of the specimen. And when I say dimensions, we mean like its length, its radius, its cross-sectional area, those kinds of things, right? And this is possible using what's called the Young's modulus. And the Young's modulus is a ratio of two units called stress and strain, right? And this is all new stuff, and you've got to try and take this in, right? Now, strain is the ratio of the extension of the material divided by its original length, okay? And it's given the Greek letter epsilon, which I'm sure you knew, that's epsilon, and it is little e for extension divided by lowercase l for the original length. Now, because these are both lengths, right, it doesn't have any units. They would sort of cancel out. So if I had, for example, a piece of wire and its original length was 10 centimeters and it extended by 1 millimeter, the strain would be 1 divided by 100, 0.01. And there wouldn't be any units because the 2 centimeters would cancel out, right? So that's how that works. So I very much recommend you highlight that. In fact, I'll highlight it with you, right? So you will need to have that now committed to memory. And you will definitely have to repeat in an exam that there's no unit for strain. Right, now turning over, the other thing we then need to know the definition of is what we call the stress, okay? And we use the word tensile stress because it's talking about a change in length. And the definition of this stress is it's the force divided by the cross-sectional area of whatever is being stretched, okay? So this stress is the force divided by the original area of the cross section. We give the stress, we denote it with the letter sigma, the Greek letter sigma, and it's basically F divided by A. And you might remember from GCSE physics that F divided by A is also called the pressure. Okay, so this tensile stress is equal to what we call the pressure. And the units of pressure that you would have done at GCSE is the Pascal. But of course, we're not thinking of it as a pressure, we're thinking of it as an extension. So we're going to use newtons per meter squared. Right, so there's two new things for you here: stress, force divided by area, the strain, extension divided by length. And it's quite easily discovered that for all materials, stress is proportional to strain. And if we swap that proportionality symbol for an equals k, a bit of basic mathematics, we get stress equals some constant times the strain, and that constant is what we call the Young's modulus, okay? And it's denoted with the capital E, and the Young's modulus for a material is the stress divided by the strain. And that's key, you know, that's going to be a big, you're going to have a big question on this on your exam, guaranteed. The unit of the Young modulus is the same as that for stress, because strain doesn't have a unit. Right, so the unit for the Young's modulus is newtons per meter squared, and here's some values for various real life materials. Right, so aluminium has quite a small Young's modulus, whereas steel has a very high one. Okay, and we'll explain what that means in a minute in terms of its stretchiness, by how much it can extend. And if you look at glass, glass has the smallest of them all, and that's because we know glass is an amorphous solid, and you apply stress to it and it breaks, it doesn't stretch. Okay, so everybody cool with that so far? Can I get a yes, please, off someone? Thank you, Patrick. Right, so what I wanted to do, just very, very quickly, a little bit of mathematics. Right, let's have a look at this question here. I've got a steel wire, and we're going to assume that when they say a steel wire, it's cylindrical. Thank you, Caitlin, I just saw your comment. A steel wire of diameter 1 millimeter and length 2.5 meters. So straight away we've got differing units. So that's your first opportunity to lose marks. It's suspended from a fixed point, and a mass of weight 45 newtons is suspended from its free end. Okay, so they've given us a weight, not the mass. The Young's modulus of the material of the wire is that. Now they've kept the units in pascals. Don't forget that's the same as newtons per meter squared. Assuming that the elastic limit is not exceeded, so i.e. it's still obeying Hooke's law, calculate the stress, the strain, and the extension. Okay, so the stress we know is the force divided by the cross-sectional area. They've given us the force, it's 45 newtons. We can work out the cross-sectional area because we're assuming a wire is cylindrical, and they've given us the diameter. Okay, so don't forget the area of a circle is pi r squared. Change that diameter to a radius, careful with your units, pi r squared it to get the area, and you can calculate the stress. Then you need to work out the strain. Well, to work out the strain, they've given us the value of E, Young's modulus, and we've got the stress, so we can divide them the right way around to get the strain. So I'd like you to have a crack at that, please. And then finally, what's the extension of the wire? And here we will use the fact that strain is extension divided by original length, because they've given us the original length there. So you're going to use all three equations I've just introduced to you. You've got to be really careful with your units. Okay, I'll give you 2 minutes to press some buttons on a calculator and see if you can get those answers for me there, right? If there's no questions, get stuck straight into it and see if you can do it. If there are questions, either say them or type them in the chat. Off you go. Ethan's on. Hello, Ethan, mate. I didn't know you were on. Are you okay? Ethan, can you hear me, mate? Yeah. Oh, no, that's Ellie. What? Elle, you all right?
I don't know. I woke up and then I could taste metal when I woke up. and I just didn't think anything of it. And then I just looked, and like the back of my throat was bleeding. So I went to look at that, so I didn't hear like part of what you were explaining.
Okay, I'll go through it again. I'm a bit worried about, you okay?
Yeah, I don't know why, because I had like I could taste metal, and then I'm like, oh, it's bleeding, but it's fine.
Okay, right. I've asked you, please. Sorry, I've lost the question. I've asked you, please, to have a crack at this question at the bottom of the page. They tell us that the wire. They give us the diameter of the wire and its length. They give us the force that's applied to it, and they give us the value of the Young's modulus, right? So what I'll do now, I'll just start going through it, okay? And they want to know first of all, they want to know the applied stress. And if you remember, as we said 5 minutes ago, stress is force divided by area. So sigma for stress is force divided by area. The force is 45 newtons. Now the area, the cross-sectional area, we don't know. But any wire we are going to assume is a cylinder. And of course, the cross-sectional area of a cylinder is a circle. So that's pi times radius squared. So you're going to do 45 divided by pi times. Now, if the diameter is 1 millimeter, the radius is half a millimeter. So that's 0.0005 meters. Is that right? Yeah. So 0.005 squared. So that's pi r squared in meters. And I've got for that 5.73 times 10, 1, 2, 3, 4, 5, 7, times 10 to the 7 newtons per meter squared. Did anybody else get roughly the same thing for the stress? Awesome, Patson. Say hello, Caitlin. Oh, Patrick. Boo. Right, now the strain, we're going to utilize this equation here to get the strain. So the strain will be the stress divided by Young's modulus, right? So the strain, I'll do it, the mess already, is the stress sigma divided by the Young's modulus, capital E. We've just worked out the stress is 5.73 times 10 to the 7, and that's going to be divided by the Young's modulus, which they give us as 2.1 times 10 to the 11. Chuck that in the calculator, and I've got roughly 2.7 times 10 to the minus 4. Now, of course, that doesn't have any units, right? Strain doesn't have units. These are both newtons per meter squared, so they've cancelled each other out. And then finally, now they want us to determine the extension of the wire. Right, so strain is extension divided by original length. So extension is the strain, epsilon, times by the original length. Now, before you type that in the calculator, let's think about the reasonableness of what we're going to have here on our calculator screen. We're talking about a steel wire, about the height of this room, 2.5 meters. 45 newtons is about 4 kilograms being hung on it. How much is it going to extend? Steel wire. That's going to be a very small amount, isn't it? In fact, it's probably going to be less than even a millimeter. So if your answer comes out as like 47 meters, you've either got a really stretchy piece of steel or you've made a mistake, right? Now, if I chuck in my values here into the calculator, I got out an extension of 0.68 millimeters, which sounds completely reasonable, so I would be happy with that if I came out with that on an exam. Did anybody else have anywhere near 0.7 millimeters as that extension? Yay! Awesome. Right, so that's a great start, okay? And basically all we're going to do now for the next half an hour is keep utilizing these equations and working around with these equations, right? Let's have a look at the next page. So same notes again now, but just reiterating what we've learned. So the reason we have this thing called Young's modulus is because different materials will have different dimensions. So stress, sigma, is force over area. Strain, epsilon, is extension over original length. And here's another way of writing that. Don't forget that little triangle there we call delta. You'll know it from your maths lessons. And it means a change. So delta L means a change in length, which is obviously just another way of saying the word extension. Sigma is F over A. And then don't forget the Young's modulus, E, is stress over strain, right? So that's just repeating it all again. The more we say it, the more likely it is to stick. So let's have a look at this question here. First of all, cross that out. I don't know why that's there. That's a misprint. Right, a wire has a diameter of 0.5 millimeters. Calculate the tensile stress if a 4 kilogram mass is hung from it. So we're working out the stress, so we need the force divided by the area. The force, here's the common mistake now. People will put in 4 as the force, and it's not, right? So this 4 kilogram mass is being hung, so the force on it is the force of gravity. So the first thing I'm going to have to do is do 4 times 9.81 to get it as a force. And then I have to divide that by its cross-sectional area. We assume the wire is a cylinder, the cross-section is a circle, so I have to do pi r squared. And then, of course, the other easy mistake to make is to use the diameter instead of the radius. All right, so everybody now just press some buttons for me. Get me the tensile stress if you're hanging a 4 kilogram mass on a wire of diameter 0.5 mil. Do that for me, please. Oh, I've made a mistake. Who can spot the, I'm going to say, deliberate mistake I have made there? Who can spot the deliberate mistake I have made? Come on. There's nothing wrong with the 4. There's nothing wrong with the 9.81. There's nothing wrong with pi. If my diameter is 0.5, there's nothing wrong with me saying my radius is 0.25. But as you've all said, I have kept it in millimeters. So it should be 0.00025. 10, 100,000. Right, let's try that again then. Okay. Oh, that's a big number. I've got 199,847,678.9. So I'm going to be really lazy and just call it 2 times 10. 2, 3, 4, 5, 6, 7, 8. 2 times 10 to the 8 newtons per meter squared. Anybody agree with that? Yeah, nice one. Right. So, next question. Nylon has an ultimate, which means when that's about to break, tensile stress of 7 times 10 to the 7 pascals. Don't forget, that just also means newtons per meter squared. If a nylon rope, like those used in mountaineering, is 1 centimeter thick, I'm not going to make the mistake again of my units. Okay, so that's 0.01 meters. Calculate the maximum weight of the climbers that it can hold without breaking. And then how many people would this represent, assuming that an average climber, plus all of his or her equipment, has a mass of 80 kilograms. Right. So I know the stress, I know the diameter. So I'm just going to rearrange this now to work out the maximum force, i.e. that's the weight. Then I'm going to divide that by gravity to work out the number of 80 kilogram people can hang on that rope. Give yourselves 2-3 minutes to have a crack at the mathematics of that, please. So don't forget, all you're using here is one formula, getting the units right, and pressing bits of plastic. All right, so have a little go at that one. Okay, so see if you agree with me. The cross-sectional area is pi r squared. It's a rope, it's cylindrical. They tell us that it's 1 centimeter thick, so that's the diameter is 1 centimeter, so the radius is half a centimeter, so that's 0.005 in terms of meters squared. There's my pi r squared. Chuck it in, I get that. If stress is force divided by area, then force is the stress times the area. They give us the stress, I worked out the area, I multiply them together, and I get that in newtons, right? So that's the maximum weight that it can hold without breaking. Anybody agree with that? Awesome. Thank you, Caitlin. How many people would this represent? So to turn this weight into a mass, divide it by the force due to gravity, and that's going to come out as 560-ish kilograms. And if we assume one person is 80 kilograms, then that's about 7 people, which again sounds totally reasonable, right? It's not going to break if you just have 2 people on the rope. I'm sure you've all been on a rope swing with your mates. The rope doesn't break if a couple of them jump on it. And if your answer came out as like 3,000 people, that's probably unrealistic as well. For 7 people, sits okay with me. And that's a pretty juicy exam question. But again, all you did was use one formula and get your units right. And very, very quickly on the last one, you don't have to do this. I'll just do it for you. A steel wire is length 2.3 meters, and it stretches, which means its extension is 1.5 millimeters. Again, it's the units that you're going to drop your marks on, if anything here. What is the strain? So epsilon is the extension over the original length. So that 1.5 millimeters in meters is 0.015 divided by 2.3. chuck it in the calculator, and I've got 6.5 times 10 to the minus 4, and obviously there are no units, okay, because it's a length divided by a length. Everybody cool with that so far? Anybody want to speak? Okay. Ethan, you still there, mate?
Yeah.
Oh yeah, good. We got someone else on. Jacko! Hello, fella. How are you, Jack? Well, I hope you got the notes in front of you, mate. Otherwise, you're going to find this tricky. Right. So let's move on. Now let's talk a bit more detail now about the graphs of these crystalline solids, right? So before we look at this one, let's think of the amorphous solids one first. If you think about it, think of glass, right? It doesn't stretch or bend really at all. It's just going to crack. So you're just going to have, and then snaps. You can have a very, very small straight line, and then it just stops. All right. Now the polymeric solids, we'll have to talk about that next lesson. Those ones where you stretch the spaghetti and then let it go again. That's a very different type of graph, and that warrants half an hour on its own. The most common one that they assess in the exam is the stress strain graph for the crystalline solids, right? Basically, your metals. And as we spoke about briefly last time, you'll have a straight line at the start where it obeys Hooke's law, and then you'll hit a point called the limit of proportionality, where that following Hooke's law is going to start to falter. Then you'll reach the elastic limit where you're going to start to have deformation. Then you hit a point called the yield point, and beyond this is game over for that piece of metal. It's never going back to its original state. Hence, at this yield point here, we draw a dotted line, okay? And it comes back to here. And that means it won't go back to its original length. And then finally, point E is called the breaking point, where it's going to snap. So let's just read through that in a little bit more detail. So O to A is linear, straight line. That's where it's obeying Hooke's law. Everything is proportional. B to C is where you reach the elastic limit. This is where the maximum load is where it will withstand and still regain its original size and shape. But B to C is the yield point, and beyond this, it will not go back to its original length, right? I wanted to think of a plastic bag, and I haven't got one here to model. If you have a Tesco bag, and you stretch it enough, and you let it go, it just doesn't go back to how it used to look. And that's because you've reached this yield point, and you've now caused permanent deformation, right? After D, the graph curves downwards. This means that after this point, the extension will still increase even though the force is constant. We call this creeping, where the material creeps, okay? So even though I'm not adding any more weight or load, it's actually still stretching a little bit on its own. At E, the wire breaks. And then G, if we remove the weights at this point here, where it's yielding, it would go back, but it wouldn't go back to its original length. And we call that a permanent set, right? Now, on the exam, here's another version of it. It's at the very back, okay? On the exam, they'll just give you a blank set of axes, and they will say, draw a stress-strain graph for a crystalline solid or a metal, and label all the key points. And you need to know it in that amount of detail, right? You need to write down the 5 or 6 sentences to describe what's going on at each point there. Okay, so that's just something you need to learn. Learn the shape of the graph and learn what each point means. And they're slightly different to each other, but basically it's straight line, starts to curve, curves a bit more, dotted line going back, but not at the same starting point. Okay, right. Now, Everybody cool? I'll take a no as a yes.
Yeah.
Awesome, thank you. We spoke about this word ductile when we did the definitions at the start of this unit. Don't forget that just means it's a metal that's able to be drawn out into a wire, so you can stretch it and it will become thinner and thinner, and you can turn it into what we call a wire. So you need to know that. And then back to Young's modulus again. Another way of writing Young's modulus. I have my pen to show you this. So we know it's stress over strain. We know that's sigma over epsilon. We know that sigma is F over A. And we know that epsilon is extension or change in length over length. So if I do F divided by A divided by extension divided by length, I get a triple decker fraction. And you've probably heard me mention them. Oh no, I don't have it for A-level maths yet. But a triple decker fraction, an A over B over C, is the same as having the C come all the way to the top and having AC over B. All right, I'll say that again. If you have a triple decker fraction, so three things in a fraction, the one at the bottom is actually exactly the same as timesing it by the top. So here I've got F divided by A divided by delta L over L. And that can be rearranged into this much more convenient form. Right? So another way of writing Young's modulus is force times by original length divided by the product of the cross-sectional area and the extension. This is the efficient way to use Young's modulus, and 9 times out of 10 it'll be this one you'll be required to use on the exam. They will give you 4 out of 5 of these, and you've just got to figure out the missing one. So let's have a look at an example, right? I'd like you to have a crack at this one for me. A wire of length 2 meters. So I've got the length. And diameter 0.4 millimeters. So from that, I can get the area, right? Because a wire is cylindrical, the cross section is a circle. I've got the length and I can get the area. Don't cock up the units. Hang from the ceiling. So we're looking at the force due to gravity. Find the extension caused. So we've got to work out delta L. When a weight of 100 newtons, so I know the force is 100 newtons, is hung on it, and the Young's modulus for this material is 2 times 10 to the 11 newtons per meter squared. So I know capital E, I know capital F, I know little l, I can work out A, making sure I don't mess up the units. They want me to find out the extension, delta L. So it's just pressing bits of plastic, carefully. I'll give you 60 seconds. Have a go. See what you come up with. And don't forget, you're finding an extension. So if your answer is 8 miles, you've messed it up. Anybody got an answer yet? Okay, sorry. I need to slow down. I'm going to start going through it. I just can't handle the silence. So the first thing I did was I wrote out E equals FL over A delta L and substituted in what they gave me. Oh, well done, Caitlin. So they gave me the Young's modulus, 2 times 10 to the 11. They gave me the force, 100 newtons. They gave me the length, 2 meters. They didn't give me the area, but they give me the diameter. So I've got to use pi r squared. And to be honest, that's the most likely place you're going to mess it up. A, you'll forget to halve the diameter. And then B, you'll forget to change the units into meters. Like I did on purpose half hour ago. So 0.4 millimeters is 0.0002 meters. If I'm halving it to get the radius, that needs to be squared. And that's times by the extension delta L that I'm trying to find. So what I've done, I brought the delta L over here, upstairs. And this 2 times 10 to the 11 comes over here, downstairs. Right? The divide goes up with the times goes down as the divide. 100 times 2 is 200. Chuck it all in the calculator and press some buttons. And I've got 0.008 meters, which is 8 millimeters, which sits quite well. Okay. And you might think, oh, that's quite an extension, 8 millimeters, that's almost a centimeter. Think about it, it's a long wire that's incredibly thin. It's less than a half a millimeter thick, incredibly thin. And 100 newtons is effectively 10 kilograms, which is quite some weight. So 8 millimeters, I'm happy with that. Did anybody get anywhere near that? Yay! Yay. Very good. Very good, right? So that's proper exam style questioning now. So you're right up there doing what you should be doing. So we've nearly finished. Hold back the tears. Don't need that sheet. Turn over. Go to this one. So very quickly, I just want to give you just a little chat about the graphs of different materials that will have different values for the Young's modulus, right? So it'll be the value of Young's modulus is large for a stiff material, right? And the graph will be steep. The stress strain graph, stress on the vertical, strain on the horizontal. If it's very steep, that means it has a high Young's modulus and it's a stiff material, right? And of course, then conversely to that, if the graph is very shallow, it'll have a low value for the Young's modulus, and the material will be effectively brittle like glass. So you need to try and understand that. What I would like you to do now for homework are these 1, 2, 3, 4, 5, 6 questions here. Oh, and the answers are at the bottom, and you're not allowed to look at them. You're not allowed to look at those answers. I didn't know they were there, right? I'd like these properly done, right? Not a little scribble next to it. I'd like them done properly, please. So I'm going to mark this properly and put it in the spreadsheet and use it as a formal piece of data for when we need it. 6 questions about the Young's modulus, about stress, and about strain. Okay, So do those for me, please, within 48 hours. Ideally, just do it straight away. It ain't going to take you more than 10-15 minutes. And you could take a photo and chuck it straight up on Google Classroom for me. Being as the answers are on the bottom, there's no real excuse for getting any of them wrong, but I do want to see all the working out. So on a sheet of A4, you'll probably fill out one side of A4. If you can, take a photo and chuck it back up on Google Classroom. And if you can't do that, that's fine, but just let me know you've done it. No cheating, please. And that'll be it then for today. We got one more big lesson left on this unit. And then we'll have a formal assessment on the unit, and I'll have to use that data as part of your center assessed grade. So make sure you're on top of everything. Any questions for me, guys and gals?
No.
Well then, like I said, please go do the questions now while it's fresh in your mind. Chuck a photo over to me. Stay safe. I bid thee all farewell. If you need anything, email or get in touch via Google Classroom, and I will see you every Tuesday at midday for my lesson. All right, everybody cool?
Bye.
All right. Please stay safe. I look forward to seeing you all soon one day. Take care. Ta-da.
Bye.